Okay, so I am Guillermo Abramson from Bariloche, Argentina. I am another one of the organizers of this program. And I am going to tell you about our work many years ago on the dynamics of Hantavirus. It is something that didn't start here in Bariloche, but very far away from it. More than 20. Yeah. It started here in the high desert of New Mexico, very different from Bariloche. And you can see how long ago, because Luca is extremely young in this picture.
Wow. Where are you, Guillermo?
Yeah. The only one who is exactly the same is my wife.
Exactly. That is true.
Alejandra Aguirre, Miguel Fuentes, Fabiana Laguna. This is from 2004, not from 2001,
Okay.
because Fabiana was there in 2004. Rosario?
Rosario Paredes. Who is that?
Morin Ballard,
Yes. That is Brazil.
Brazilian. Fernando Albuquerque.
Fernando Albuquerque.
Very appropriate name to come to Albuquerque.
Yeah.
Paul Paris, Nitan Kenkre.
Yeah.
And this girl?
I don't
remember her. Gustavo Camelo,
Gustavo.
Ana Adriana.
And back there, this is, I think I know.
This is Roberto Iglesias.
Yes, yes.
And this one?
I mean,
Probably a student.
the Indian guy came here. This,
Who?
which one? Just close to Luca. No, this is Nitan.
Yes, this is Nitan.
No, not Nitan. Just down. Oh, that.
Brazilian.
Brazilian. Albuquerque, yes, the last name de Albuquerque.
Fernando de Albuquerque. So I am going to show you a few details of part of our work. This is our roadmap with many branches. And I will tell you about a few of these because we will not have time for all of them. And I will start with some background on the Hantavirus. Hantavirus in New Mexico is associated with the deer mouse. This is deer mouse, Peromyscus maniculatus. It's a very common animal in North America. It's the most numerous mammal in North America. And it is the host of Synnombre virus, which is one of the species of Hantavirus. It doesn't produce in the mouse any clinical disease. They have co-evolved for millions of years, but it produces a very severe pulmonary disease in humans when it is transmitted from the mice to humans with very high mortality. It's like Ebola. It's a terrible thing. Without treatment is 50%, and with treatment it reduces to 30%. The first, in quotation marks, outbreak was identified precisely very close to Albuquerque in '93, but there is evidence that the Navajo people of the region already knew about a severe pulmonary disease influenced by environmental conditions. There is Hantavirus diseases in all of the Americas, actually in almost all the world. And when we started working with this, I was particularly interested because besides the one that happens here in the southwest of the United States, in Argentina, it was discovered 2 years later that we also have a very severe syndrome associated with another one, Andes, which is hosted by this other mouse, Oligorhizomys longicaudatus. So I was particularly interested in working with Nitan and Luca on this problem. And you see in all of the countries of America, there is this is rather old actually, 2004. There are cases. These are human cases of the disease and deaths. Fortunately, it's not easy to get the disease. It's very difficult, not like COVID. There are many species. Each one of the species is associated with a particular species of mice all over the Americas. The one we were interested in at the beginning was in Nombre, here in the North American Southwest. And Bariloche is here, the region of the Andes virus. But there are many more, as you see, and probably much more than these ones. So as I mentioned, the disease infects chronically the mice. It's an infection of mice, of wild animals. There is horizontal transmission within the population of mice mainly by aggressive behavior. So most of the infected mice are adult males, which are the ones that fight, but there are also female affected. And there is a sporadic transmission of the virus to the human population, living close to mice by inhalation of aerosols, secondary aerosols from urine and such. Typically, mice do not bite people. It is from, for example, cleaning places that have been abandoned for a long time. You remove, you start to dust, and the dust blows, and you get the virus in your body. And the only one that can be transmitted from person to person, it seems to be the Andes, the one that we have in Bariloche. But it is mainly an infection of the mouse population, and that's what we modeled. So let's start with our first model, which is the simplest one, which was based on our talks with the experts in the field, zoologists, most of them, who had been working since the outbreak in '93, and they had been studying the wild mice population for more than 10 years, checking the number of mice, the number of infected mice, number of parameters. Those are the ones, those are the people that told us about the things that I mentioned, that most of the infected mice are adult males, etc. And these details, which are the main characteristics that we heard about and which we use to base our basic model. There is a strong influence by environmental conditions. There is a sporadic disappearance of the infection from the population. So this happens as outbreaks, even for the mice. And there seems to be a spatial segregation of infected populations. So in some places in the landscape, the mice population are chronically infected. And some other places, the infection disappears and then it spreads again from this refugia that they call it. So our model aimed to capture these ingredients. Mainly, we aimed at using a single control parameter in our model to model the environmental conditions and to have these two as emergent properties of the results, of the dynamics. This is the basic model without movement. So it's like the mean field basic model. It's a standard susceptible and infected model, like Kermack and McKendrick, but which incorporates the details that we know about the biological system. I will tell you a few of them. For example, all of the mice, M is the sum of the two, the susceptible and the infected, the total population. So all of them contribute to the population dynamics. Births are produced from all of the mice. There is no vertical transmission. All mice contribute equally to the, all mice are born susceptible, so to say. There is no difference in the death rate of mice because it doesn't produce any disease in them. So C is the death rate is the same for all of them. They compete with each other, of course. There is a probability of transmission which is proportional to the encounter rate, proportional to, in the mean field, proportional to the product of the densities. And the environmental parameter is this one, K, which is in the terminology of ecology, a carrying capacity, the maximum number of mice that can be in the system. So what is the result of this model? What are the solutions? No, there is no disease. There is no evolutionary pressure for them to get rid of the disease. They coexist, like we coexist with so many other virus and bacteria. So the result of the dynamics is straightforward. It is a transcritical bifurcation at a finite value of the carrying capacity. So this is nice. We have the parameter that is controlling the effect of the environment actually produces a transition between the disappearance of the infection and the endemic, so to say, persistence of the infection. So K is the carrying capacity. In the supercritical cases, is endemic. In the subcritical cases, there is extinction. This scenario depends critically on the details that I mentioned in the previous transparency, in particular on this one. The same model, but with vertical transmission. So at least some mice are born infected. Look what happens. This is the case without vertical transmission. With vertical transmission, you lose the positive value of the critical carrying capacity. So the critical carrying capacity becomes 0. So it's actually no critical carrying capacity. There is always endemic. So these details are important in the actual outcome of the dynamical model. So we had what we wanted. And of course, we wanted to go further. The first thing we did was to modulate in time the carrying capacity, because this is what can produce the outbreaks and disappearance of the infection. And if you do that in a cartoon, for example, modulating the carrying capacity like this, you have an outcome that follows the carrying capacity. If the carrying capacity is above the critical, which is this blue line here, you will have some oscillating value of the infected population. But if it becomes subcritical because some bad environmental conditions, such as a drought, you have exponential extinction. And when the conditions change again, you have recovery from that extinction into a new endemic state. And if you have some extraordinary events which produce much better environmental conditions for the mice because of a trophic cascade, more precipitation, produce more food, which produce more carrying capacity, which produce more mice, you will also have more infected mice. So this kind of scenario is what we thought could be the responsible of the field observation, the sporadical disappearance of the disease and the outbreaks, controlled by the carrying capacity. And the critical connection between our cartoon and the actual results is this trophic cascade that in the North American Southwest is triggered by the El Nino environmental oscillations. El Nino produces increased precipitation in the region of the Southwest, also in the region of Patagonia. It produces drought in some other places like Central America. But increased precipitation is correlated here. Precipitation is correlated positively with vegetation and with population of mice. This is from a work of one of our collaborators there. And in the years when Hantavirus was discovered in the Southwest, which was 93, I think, yes, 93. You can see that there was the peaks in sea surface temperature, which is the black line. The peaks are El Niños, this one. And the dips are La Niña. The events between Niños are called Niñas. So there was a wide and severe El Niño a couple of years before the outbreak. The peaks produce an increased precipitation, and with a delay, you have the outbreak. This is not in mice population. This is the number of the human disease. This was the discovery of the disease in 93. Here, delay is the time it takes trophic cascade to propagate from the environmental change to the spread of the disease in mice and eventually to humans, also an outbreak of the human disease. So it was very nice. In one of the sites, I tried to make the connection even tighter. This is the big El Niño of 98. I don't remember. This was so long ago that if you ask me something, I'm not sure I will be able to answer. But I know this is the big El Niño of 98, and mainly I know it because I left it. So this is from one of the sites in New Mexico, SUNY site, which is in what? Yeah, it was very severe. So let's start on the left side of this. You have some fluctuations in the population. Black is total population, blue is susceptible population, and red is infected population. So you have some fluctuations, and there is also some fluctuation of the infected population. This is real mice from the field. And then you have a fall in the total population, and at some point it becomes subcritical. This horizontal line is the critical value of the population related to the critical carrying capacity through these parameters, which I fitted from some parts of this curve. I think it was from the exponential growth where it could be determined. And when it starts to be critical or subcritical, you see that the infection starts to disappear. Eventually, it disappears completely for some time. And then you have the El Niño, which produces an exponential increase of the population to a new value of the saturation of the carrying capacity. And with a delay, because it needs time to propagate into the population, you have an increase of the infected population, and then it stays supercritical above the horizontal line. So the infected population also remains positive. So it seems to work. Yes, tell me.
On the y-axis is numbers.
Numbers, yes.
So this
or dense.
No,
not numbers. It has to be densities because it's smaller than 1.
Oh.
So this is probably mice per hectare.
Oh, okay, yes, okay.
This is the thing that they measure, and they use devices that I will show later.
So those are old data? Or?
Data. These are data from the field. Yes, these are data from the field.
Guillermo, one thing I don't understand. So, because critical population, but then you have some red under the line, which is critical.
The line is the only thing that is not data. It's derived from our model. Well, but the value of B minus C is derived from the exponential growth. The carrying capacity is the one given by our model. The critical carrying capacity is connected to a critical population. So if you have less than 2 animals per unit area, the infection disappears. The density is not enough to keep the horizontal transmission. So that was our first approach, the mean field model, but we know that there must be some extended dynamics because it is known from the field. So we extended our model in space in two senses. First, we made the carrying capacity spatially extended because of variations of the landscape. And we also added a diffusive transport for mice. Why did we put diffusive transport? Because it's the thing that we know how to calculate. And related to that, I want to show you what Okubo and Levin say about diffusion in their book on diffusion and ecological problems. Diffusion in ecological problems has 3 categories of wrongfulness, and we hope that we used our diffusion in the first sense. Wrong but useful, meaning that the simplest diffusion models cannot possibly be exactly right for any organism in the real world because of behavior, environment, etc. But they provide a standardized framework for estimating one of ecology's most neglected parameters, the diffusion coefficient. It can also be not necessarily so wrong, because you have some transport which is kind of diffusive like, or it can be woefully wrong, and we hope it's not the case for our mice. This is from their book, which is very nice. So we analyzed that partial derivative extension of our model, and we found that concentrating the above critical carrying capacity in space, we of course can have this refugia that the biologists were speaking about. The refugia should be related to it is the carrying capacity, so it should be related to the resources available to the animals, which not only change in time, but also in space. New Mexico and the North American Southwest is mostly a desert. There are woods in the heights with fruits that the mice use as a resource. And this is a cartoon, for example, like in Argentina, region vegetation that can be analyzed from satellite images, can be related to the especially heterogeneous value of the carrying capacity. So in this case, for example, you would have refuges in this. This was our proposal, and they eventually measured it, knowing what are the resources of the animals. They call this the Sky Island Refugia because they are high in the mountains. And they correlated this refugia to the number of cases of Hantavirus in pulmonary syndrome, the disease in humans, which is highest when the carrying capacity is larger as measured by several. This is a combination of several bands of satellite photography. It's intensity of resources available. Yeah, it's mainly the vegetation because they eat fruits from trees and other plants. The blue is nothing. And then the green, the yellow, the orange, and the red are the worst places. The red places are the places that serve as a refuge between bad years of.
Can you, I mean, did they didn't put the location of the human cases? No, because they take
No, but you see the four corners. It was Zuni, the one that I showed you, is like here. And Albuquerque is here. La Niña is bad for mice because it produces a drought in the region. So all the red adoras have disappeared, and you have this blue channels separating the refugia. That's why I presume they call them island and sky, because they are high in the mountains. So we have this extension of our model with diffusive transport in a reaction system. So we have that partial differential equations that I showed, and you can imagine that the way in which the infection spreads when conditions change is driven by a wave, like in Fisher's equation. Actually, the equation for the total population is Fisher's equation. So you expect to have traveling wave solutions of it. You know that there are, I know about it, but it's kind of a miracle for me that there are traveling waves in a parabolic equation. It's with the first derivative of time here. So I showed you before this fluctuating value of the carrying capacity produced an extinction, but this extinction in the midfield was exponential. So eventually you recover from that epsilon of infected population that you have. This cannot happen in reality because when
so this is the field for N in your model.
Yes.
Plus MI.
Yes, and it is just Fisher's equation. So in the real life, extinction is forever. So if you have recovery of the endemic infection everywhere, it has to come from somewhere else. And the way it comes from where? From the refugia. And the way it comes is through traveling wave solutions of this. And if you solve it in susceptible and infected, you have that there is a wave of susceptible, and with a delay behind it, or inside it, if you wish, there is a wave of infected. So these two, this is in one dimension, with the refugium to the left and empty space. So this is extinct to the right. And behind the mice front, you have a traveling wave of infected mice, right? We can calculate the speeds of these fronts, and it happens that, well, the susceptible one is the Fisher velocity, but the infected one has a velocity, the infected population, the infected wave has a velocity that depends on the carrying capacity. So there are different regimes of propagation of the infected wave, depending again on the carrying capacity. There are two regimes, one with a delay that goes asymptotically to a constant, so the two waves move at the same velocity. And if the carrying capacity is a little smaller than another critical value, so there is a new critical behavior in the system. Below that critical value of the carrying capacity, the infected wave lags behind progressively. I have no idea if this thing has been measured in the field, but it was one of the results of our analysis. What they did measure was the waves. And actually they measured them. This is in one dimension because it's easy to analyze. And even if we thought at the moment that the correct analysis in the real world should be two-dimensional, there are cases of populations that are almost one-dimensional because they know of populations. This is a mountain near Albuquerque, and the mice live along the canyons where they have most of their resources. So they put traps along this canyon from the cliff near the top of the mountain to the valley below, and they measure the mice population along these tracks. You can see that there is a change in the vegetation, which produces a change in the available resources. So there's a change in carrying capacity with the distance from the left, which is with altitude. So the change in carrying capacity during the seasonal changing of vegetation along the altitude gradient in the mountains produces an expansion and contraction of the population that moves from places where they have the best resources to when they start to deplete or lack those resources, they move to suboptimal places. They call them optimal resources and suboptimal, less palatable resources. And you see that the total population along several years measured there in that mountain grows and falls and then grows again, but following a corresponding change in the range along the canyon where they measured. The range, the range from the top of the mountain to the lower range where they find mice, right? This is measured from the top of the mountain. So you it's covered. Yes, because zero, this is measured from the top of, I remember that. So zero is the top of the mountain. They cannot go beyond that. But they extend down slope. When do they extend down slope? In July. And then in July, they start to go again. And then something happens. This is a problem of field work. It's always noisy.
Why was the first page to change that range?
The availability of resources. Yeah. Because they eat the nuts of the pines, of the juniper, of the oak, and the change in the availability of those resources is what they make them move and reproduce also, because you have more population here. And if you divide population by linear range, you have that they move almost at a constant linear density. They expand and contract at the linear density, except for these 3 points. So in our model, we can produce something like this, moving the carrying capacity along the canyon, the linear coordinate, and also in time, following the seasonal variation. And in some regimes, you can reproduce this change of population at a constant density, the black line here. The red and the blue are other regimes. So this seems to be what we call the adiabatic regime, but I don't really remember why we called it adiabatic. Do you remember? But in some regime, you have this narrow growth and shrink of the population at a more or less constant linear density. That was observed in the mountains. So after our analysis, they continued measure, and actually they measure the speed of these waves in several places.
Your model, have you measured? So it's a parameter of the model, no? The diffusion coefficient.
Nobody knows. Nobody knows. What, no.
But you have not fit it to some data or whatever.
We try to do it. I will tell you a little more later. If you ask an ecologist what's the diffusion coefficient of this animal, they have no idea, except if they are Okubo or Levis.
So, but what is the definition of diffusion velocity? I'm sure
No, it's velocity.
yeah.
That's why I put not really diffusion. It's the velocity of the front. And they also correlated the distance from the resident of, this is for humans, this is animals. And these are cases of human disease, number of days from the first human disease. And in the vertical axis, the distance from the residence of that person to the nearest refugium that they identify through satellite imagery. And you see that there is a very nice linear relation, so there is a speed here. And that speed is probably the speed, the velocity of the red one in our body. This was much later after we left Luca, I think. You remember that when I visited again in 2012, they were building these trucks.
So this is the velocity of the front.
Yes, the velocity of the front.
For this velocity of the front, you can obtain the diffusion coefficient.
Yeah, probably. I haven't done that. Yes, you could.
But then you need to look at the actual value of that carrying capacity. That has units and it's always relative, so it's probably.
Yeah, well, some combination of both.
Yeah.
And it is, of course, related to other parameters of which nobody has no idea. So in many of these problems, there isn't a value of a parameter, there is a phenomenology. And you try to explain qualitatively the phenomena that are observed, disregarding the exact values of the things. But it's good that that's the phenomenology seems to be well explained by our model and extensions. What comes? It's already, when did I start? 11:30. Another thing that we did was an extension to include other species of animals, because mice population live in competition with other species of animals for the same resources. So if you have, and each hantavirus is associated with a single species of mice. So if you have another species that is not a host, M is the host, and you have a Z, which is not a host. I don't know why we use C, but I remember that Anita called them zebras.
Yeah.
You have like a dilution effect. So you have the same resources diluted into two species. So the effect is similar to having less resources for the host, and you can have extinction. You can have extinction of the infected population, driven by the abundance of the alien or the zebras species, the aliens carrying capacity. I remember that when we wrote the paper, this was Ignacio Peixoto. When we wrote the paper, I argued that it was not exactly a dilution, but I don't remember why I said that. I should read again the paper.
So the carrying capacity is equal for both, no?
You can, in this diagram, you have a range of carrying capacity of both.
No, but
So you can be within the subcritical value of the carrying capacity of the host, but if the carrying capacity of the aliens is high, you will be outside of the of the prevalence region.
Go back to the question. So
It is the solution of this one. Yeah, this is the carrying capacity that drives the infection to extinction. But you have also this one, the carrying capacity of the zebras, that competes with the one that keeps the infection alive.
If you eliminate cell there adiabatically, then yeah, right. The case will be different. You eliminate cell, then how
You mean if you do
derivative of cell is equal 0, then
if you slave this one to this one, yeah.
Well, yeah, this is still
Yeah, probably we did that. I don't remember exactly. But this is actually easy to analyze exactly. The bifurcation is like this. So the transport and the diffusion coefficient. If you analyze the mean square displacement with the idea that you will be able to compute the diffusion coefficient from the behavior of the mean square displacement as a function of time, you find these things, that it grows and then it saturates. We were very surprised because we were expecting, because our model had diffusion, we said then the animals must behave diffusively, but it didn't. When we asked our colleagues what was happening, they said, of course, because they live in home, they have home ranges, like people do not diffuse in the world. So you have a growth of the mean square displacement and then a saturation to some size of the home range. And we observed this in New Mexico and also in Panama, where our friends Gerardo Susan and Erika Marce had been measuring the year before. So this. So with Luca, we had the idea to make a theory of this, to try to find the diffusion coefficient, or at least to understand what was happening. So on the one hand, we have diffusion within home ranges. So we had to put some constraint on the walks, the random walks that the animals were performing. But then we realized that the measurements were done within some very prescribed region of space. So we might have had animals coming into the region and then moving outside. So their home ranges could be overlapped with the window of observation that we supposed a square, but was actually a circle. You remember the webs? So we tried to put both of the constraints together to have both the actual restriction of movement of the animals and the limited window of observation. This is how they measure them. They capture them in the field in traps. So this one is actually more restricted than in his home range. Poor thing. Yeah, they release. Poor guys. Even if they are infected.
Were the animals tagged?
Yes. They do them incredible, nasty things. I went with Gerardo and Erika to the field, and yeah, they take blood from places that you wouldn't imagine. Such as, for example, behind the eyeball. Yeah. Only a biologist can be so. So we were able to do this in a model, at least. The first thing we assumed was that we put the animals in a box but then we relax it a little bit and put the animals in a harmonic potential, like mice on springs. And I think we did another potential that we calculate exactly also, Lorentzian or something like that.
Also some logarithm.
Yeah.
Okay.
So in several cases, we were able to model this analytically, having a set of homes, which are these, in this case, these harmonic potentials. Inside each one of those, an animal moving diffusively. This is a Norstein-Uhlenbeck process, so the stationary probability will be a Gaussian that can be calculated exactly. And superposed on that image, you have a window, the white part, a window of observation, a window of size G. So we were able to analyze the Fokker-Planck equation, describing the temporal behavior, the spatio-temporal behavior of the probability distribution of mice moving. You have a random walk bounded by a box, or in that case, a harmonic potential, but you observe only part of it. So to calculate the mean square displacement, you have to take into account that you do not observe the whole system. So you have an additional integration in this region to calculate the mean square displacement. And the mean square displacement that you calculate, of course, depends on the shape of the potential, which is U, on L, which is the characterization of the home ranges, which in this case is the standard deviation of the Gaussian, say, and on the size of the window you observe. So we ended up with a picture like this, where the mean square displacement can be plotted as a function of the ratio between the home range size and the observation window size, L over G. And it is a function like this that grows and then saturates. And for different models, it's very similar. We made simulations of this, and it also worked. So a box is a square box. Harmonic potential is the Norstein-Uhlenbeck process. The asymptotics, I have no recollection of what it was, but this was very similar also. And I have the impression that there was another one with the logarithm,
No,
as you said.
Yeah.
Yeah, but somehow this is the ones that I could rescue from our work. So this was very nice. Why? Because this is the asymptotic value. So it would be the saturation that you can measure in the field. So this is something that can be measured with an error. So if you measure that, you come to this line. All of them are very close together, so it doesn't matter exactly if your mice are harmonic or moving freely in the bottom of a box, like poor Peromyscus there. And from that point, you get the size of the home range, because the grid, you know the size. So you can derive the home range size, which is something very difficult to measure without following individual animals, just from mark recapture measurements they had. They already had this for many years, more than 10 years. So this was also very nice. There is also, our model up to what I told you was deterministic, smooth, analytical, in the sense of the analytical functions, differential equations. But you have seen that the populations are very fluctuating because the number of animals is small, so fluctuations are large. So it would be nice to have a stochastic formulation of the problem, formulated as a master equation, and to analyze the phenomenology that this stochasticity can produce in the in the dynamics of the disease. You can have extinction, like in the mean field models, perhaps different. But you can also have, you will have certainly fluctuations that you don't have in the mean field models, and you can characterize fluctuations from the statistics produced by the master equations. But eventually you can have a new phenomena, and indeed you have oscillations. But this is something I'm going to tell on 17th October, just before the connecting micro to macro in epidemiological models. So I will save that for
Since I'm not going to be,
this afternoon. I can.
Individual model, and then you go to the microscopic dynamics.
No. Yeah, you do a macroscopic dynamic like that. I don't have the master equation here, but I have the nice phenomenon that I will show you. Which one is it? This is for some value of the parameters where you have damped oscillations. The mean field model is the black line, and the red line is the average of 10,000 realizations. It's very good. Even though they are fluctuating, you go to the same fixed point. And then without space. If you look at a single realization of those 10,000, you have this. So you don't only have fluctuations because of the stochastic nature of the dynamics, but you also have something that has a very well-defined frequency. If you show that to any field epidemiologist, they will say this is an oscillation. Even though the system is not periodic, it is an oscillation that you can call a stochastic oscillation. And from the master equation, we were able to do a theory to characterize this oscillation. Calculate the frequency, the power spectrum, and even to see the conditions in which the number of the size of the system is relevant. This is the power spectrum for different system sizes. And the analytic curve, which is derived from a Van Kampen expansion of the master equation. This is the black line. Works very well, even for very small systems. This is like the current capacity of the system. Or you can connect. Yeah, or you can even connect remotely. So for now, for today, that is all. Thank you very much. And
this is absolutely not possible to do something like this because that's Hantavirus.
yeah, please do not tell anyone. We have to stop the recording. Because of course I was not allowed to handle the animals. No, but this is not a Hanta mouse. This is
from mice to human, no? Or this is...
no. This is another species.
So
They didn't allow.
Any species can infect from mice to human.
No, only the Peromyscus. Only the Peromyscus. There are some other species that can get infected, but it's not the main host and reservoir of the virus. And this is one of the zebras, a competitor of the Peromyscus. This is called a pocket mouse. I do not know if it's because it's so small that they allowed me to handle with gloves.
Very good. So any questions, comment? Please.
When you said obviously with the drought, obviously the resources become finer. So would you say you can see it almost like a correlation that it pushes the mice away to find the resources? So then you might see peaks of the infection in those new places.
Yeah, there is movement and there is also death of mice. They die from lack of resources. Actually, the population, you can imagine that the whole time is spread along the landscape. And when there are enough resources, they are everywhere. When the conditions are bad, it is not that they come back to the refugia, they just die. And the population is kept alive, the extended population is kept alive in the refugia. And when conditions are good again, they spread again into the empty space. This is what they tell us.
From the potential, I have missed it, but you have two parameters, which is like the land scale of the home. How big
Yes.
is the home. How do you handle the fact, like the alignment between the G region, the region of observation, and the location? Like, oh, you consider them as different potential, or U1, U2, U3 is like different cases?
Yes. Each mouse has a home. So each mouse has a different potential. And you have to calculate the mean square displaces, the M here has two integrations, one over the population and one over the size of the grid. Remember that, Luca?
But yeah, the third integral is about the density, where the location of the.
Also on the position of the of the parabolas.
We make it uniform. So that's essentially.
You say, yeah, it's quite probable.
But if you want, if you have information on that, you can put it in. Then it doesn't become so nicely analytic like this.
Yeah.
Yeah, but I guess it's okay. Yeah, okay. I missed that point.
Yeah, if it is uniform, you can calculate the mean square displacement analytically for a shape of the potential. In the case of the parabola or the square well, you can.
There are many studies correlating and linking.
Yeah, there are many. Yeah. Because of this effect of, they call it the trophic cascade. When there is more water available, there is more vegetation, so there is more food available for the animals. And all these zoonotic diseases are correlated with El Niño. There is a Niño now starting. So next year there will be more Hantavirus cases probably.
I typically know the delay between Nino and
There is, 1 year. It is 1 year. Yeah, they found. Remember the one that I showed you with, which was the correlation between cases and this one. This is on ERT, and this is ERT +1.
This goes for the case of the
Mice.
mice.
Yeah, but the contagion rate from mice to humans is immediate. When there are more mice, there are more cases. The same year. The delay is between precipitation and the population of mice, because the vegetation has to increase, produce fruits, the mice population have to reproduce, so this takes 1 year. And it is more or less what you see here. This was 93. Well, this was very wide. This was 98, and the peak.
Yeah, but these are only 2 points.
I don't have more points. The disease is very rare, so the data are scarce. Probably that's why we stopped working on this. It was not easy to get good data.
Anything else? Okay,
Thank you for coming.